Whenever you go to an exhibition, you will probably receive this stamp of invisible ink. This stamp is necessary when you re-enter the exhibition, where it illuminates blue when shone under ultraviolet light. As it can emit light of its own when stimulated by incident light, the invisible ink is thus known to be fluorescent. Fluorescence works based on the principles of electron configuration. As mentioned previously, electrons fill up orbitals based on three rules of electron configuration: Pauli exclusion principle, Hund's rule, and off-bulb principle. Electrons follow all these rules to obtain a configuration that uses the least energy possible. The orbital occupied by the last electron thus has the highest energy level and is also known as the highest occupied molecular orbital, or HOMO. The orbital of the next energy level is the first orbital to possess no electrons and is thus known as the lowest unoccupied molecular orbital, or LUMO. The energy levels of each molecular orbital can be determined using computer simulations, where the energy levels are indicated in electron volts, or EV for short, where 1 electron volt is 1.602 times 10 to the negative 19 power joules. While electrons stay in a configuration which uses the least energy possible, also known as the ground state, the electrons can be excited and jump to the next energy level if given a specific amount of energy. This energy is determined by the difference in energy between the HOMO and the higher energy orbitals. Any specific amount of energy equal to the differences can excite the electrons in the HOMO to the respective orbitals. But for this case, we will focus on the LUMO. This energy can be supplied through particles with wave-like properties, such as photons of light for the case of invisible ink. The energy supplied by photons of light is determined by the Planck's constant multiplied by its frequency, or Planck's constant multiplied by the speed of light divided by its wavelength. So, for this scenario, the wavelength of the incident photon is 206 nanometers. Now that the electrons have been excited and promoted to the next energy level, the electron configuration no longer complies with off-bulb principle, and the electrons would return to the ground state configuration by losing energy. Some of the energy dissipates off as heat, resulting in the energy of the emitted photon being lower than that of the incident photon. Suppose that 20% of the emitted energy has dissipated as heat. The emitted photon will have 4.8 eV of energy, or a wavelength of 258 nanometers. By considering the factors of energy, this means that the emitted light has a lower frequency and a longer wavelength than the incident light. Fluorescence happens instantly and lasts a few nanoseconds. The emitted light is electrons being repeatedly excited and jumping from the HOMO caused by the incident light. When the incident light is removed, so does the emitted light. Back to our example of the invisible ink. It is excited by incident ultraviolet light with a wavelength of 350 nanometers and emits blue light with a wavelength of 450 nanometers. Pause the video now and try to find out the energy of the incident and emitted photons.